All right, welcome back. So in the last lesson, we learned how to do the algebra of matrices, where we learned how to add matrices, subtract matrices, scalar multiplication of matrices, and then we spent a lot of time on matrix multiplication. It seems like maybe that's the most important out of those matrix operations, is how do you multiply a matrix times another matrix? And I'm going to start this lesson with a warm-up problem, but this is going to be a lesson about the inverses of matrices. All right, so I said that I was going to start us with a warm-up problem, and here it is. So just to make sure that we're all comfortable with matrix multiplication, I'd like you to pause the video and give this a try. So this is a matrix times a matrix, and remember last time, usually when we had this kind of problem, I would take the two matrices that we're multiplying and write them side by side. I think that helps me match up the right rows and columns. Instead of the way the problem was phrased, had them kind of separated. I like seeing them side by side. That's just my own personal preference. And then that helps me see, we're going to look at row 1, column 1, row 2, column 2, etc. So to get this first entry, it's in row 1, column 1. So we're going to do row 1 of A and column 1 of B. So we do 3 times negative 2 plus 3 times 3. Up here in the upper right, we do 3 times 1 plus 3 times 5. This is a 2 by 2 matrix that I'm forming, even though it looks really wide. That's okay. That's just the way we write it sometimes. 2 times 3, and this is going to be 1 times 1 plus 2 times 5. All right, so we need to simplify this, and this is negative 6 plus 9, 3 plus 15, negative 2 plus 6, 1 plus 10. So final answer then is 3, 18, 4, 11. This 2 by 2 matrix is the answer. All right, so if you need to, you could go back and review matrix multiplication from the previous video, but I just wanted to do this one warm-up problem. The topic that we're talking about today involves matrix multiplication, so we want to make sure we're good at this, especially for this 2 by 2 case. We're going to be focusing a lot on 2 by 2 matrices. Okay, so let's see. I'll start this lesson officially with a definition. The n by n identity matrix, which I'm going to underline that, denoted In, or I, is the matrix with all ones in the diagonal entries from upper left to lower right, and zeros elsewhere. So let me show you some examples of this. This is a specific matrix that turns out to be pretty important, so it gets its own name, the identity matrix, and it has its own notation. It's written with a capital I, or a I with a little subscript n. So, for example, I2 is a 2 by 2 matrix with all ones in the diagonal entries from the upper left to the lower right. So the upper left of this to the lower right, those are going to be ones, and then everything else is going to be a 0. So that's the identity matrix I2. I3 is a 3 by 3 matrix with a similar structure. From the upper left to the lower right, we put ones. I usually write those first. And then everywhere else, we put zeros. And let's write I4. I4, it's a 4 by 4 matrix. It's a square. And from the upper left to the lower right, we need ones along that diagonal. And then everywhere else, we put zeros, making sure that this is 4 by 4. So those are 3 examples of the identity matrix for n equals 2, n equals 3, and n equals 4. But really, this could be established for, n equals 5, 6, 7, 8, really any positive integer. And what winds up happening is sometimes we're working with matrices and it's kind of clear what size matrix we're working on. And that's why sometimes instead of calling it I2, I3, I4, sometimes we'll just call it I. And the size or dimension will be kind of clear from context. If everything that we're working with in a problem is 2 by 2, and we say I, then we assume that it's I2. Now, why is this matrix useful? I'll tell you a fact about this matrix. Let A be any n by n matrix. We call these a square matrix because number of rows and columns are equal to each other. The fact is, when we do matrix multiplication with I, like A times I, it turns out that it just equals A. And if you do I times A, you also get A. All right, so I guess I would say as kind of an analogy or a comparison, it's a little bit like when you're multiplying real numbers and you multiply a number by 1. Like if I do 5 times 1, I get 5. If I do 1 times 5, I get 5. So the identity matrix kind of serves that role, but for matrices. A times I, you just get A. I times A, you just get A. So multiplying by I doesn't change the matrix. You start with A, you still have A. You start with A, you still have A. And that's why it's called the identity. It's basically, if you want to get technical, it's the multiplicative identity. By the way, this matrix I is unique in this sense. There's no other matrix that does this. There's no other matrix that has this property for all square matrices A. So this section is called inverses of matrices. We had to establish what the identity matrix is first, but now we have another important definition. All right, so let A be an n by n matrix. The inverse of A, let's underline that, the inverse of A, denoted A with a little -1 up there, is the matrix if one exists such that A times the inverse of A equals I, and A inverse times A equals I. So that's the definition of the inverse of A. We sometimes pronounce it A inverse. And by the way, well, I'll just give you a chance to see that, give you a chance to write that down. All right, I have a couple of things to say about it. One is I want you to understand that even though we write a little -1 up there, it's not an exponent. It's just the notation that we use for inverse. I mean, we've seen this before when we do the inverse of a function. Think about like the inverse of sine or the inverse of cosine or just the inverse of a function f. We always use the -1 up there. It looks like an exponent, but we understand that it's not. Now, this is not a function, right? It's a matrix, but we still use this notation. Now, in what sense is this the inverse? Well, the basic idea is that if you multiply a matrix times its inverse, you wind up just getting the identity matrix. And also if you do it in the other order. To give you an analogy, I like to compare some of these things to what we know about multiplication of numbers. These are multiplication of matrices. But as an analogy, if I had, let's say, the number 5, is there a number that when I multiply 5 times this number, I wind up getting 1? Yes, there is. It would be 1/5. 5 times 1/5 is 1. 1/5 times 5 is also 1. That's an analogy. That's not exactly what we're doing here, but we're kind of doing the matrix version of that. A times something equals, it's not really 1, but we said that the identity matrix kind of serves that role for matrices. So maybe you can see why it's called the inverse. Now, in parentheses, it says if 1 exists. So let's talk about this. A couple of things I want to say right away is that not every matrix has an inverse. Oh, you know what? Another thing, I don't think I'm going to write it down. I'm just going to point something out. This definition is only for square matrices. It started by saying that we have an n by n matrix, so the number of rows and columns is the same. But even still, if you have a square matrix, you could still say that not every matrix has an inverse. If A inverse exists, we say A is invertible. Now, in this lesson, I think we're mostly going to focus on 2x2 matrices, but you can just keep in mind that most of what we're saying is going to also apply, well, a lot of what we say is going to also apply to larger cases as well. All right, let's move. I'm going to move the definition away to make some room here. So we know the definition of the identity matrix. We know the definition of A inverse. And I'll show you an example of a matrix and its inverse. If A is the 2x2 matrix 3, 1, 4, 2, then A inverse. I've already found A inverse, and right now I'm not going to tell you yet how I found it, but A inverse turns out to be 1, -1/2, -2, 3/2. All right, it's a 2x2 matrix. Now, I didn't tell you how I got this. I'm just telling you this is the inverse of this matrix. But we could check it. We could verify my claim. I claim this is the inverse for A. It's because if we multiplied them, if we put them side by side and multiply them, let's see what we get. Let's actually do it. Let's actually write it all out. We want to see I mean, allegedly, if this is the inverse, then that would mean that when we multiply these, we should get I, the identity matrix. Let's see, 3 times 1 plus 1 times negative 2, 3 times negative 1 half plus 1 times 3 halves, 4 times 1 plus 2 times negative 2, 4 times negative 1 half plus 2 times 3 halves. Okay, so let's see what we got. In the upper left, that looks like 3 minus 2, so we got 1. In the upper right, that looks like negative 3 halves plus positive 3 halves, so we get 0. In the lower left, 4 minus 4 is 0. And in the lower right, negative 2 plus 3 is 1. So I'll just put a check mark here. It does check out. This is the identity matrix. Now, I could show you how to derive this inverse matrix for, you're given this matrix A. How do you find this inverse matrix A inverse? I could show you how I found it, but instead, I think what I'm going to do is I'm going to skip the specific example, and let's search for a general formula instead. Let's try to find like a general rule. If I'm given any 2 by 2 matrix, what is a formula for finding the inverse? And we're going to derive this. So once we know how to find the general formula, then we'll be able to answer any problem, not just this one. So the question is, if A is a general 2 by 2 matrix, any 2 by 2 matrix, well, how do we write like a general 2 by 2 matrix? I don't want to put numbers in there, right? So we put letters in there. We're going to call this A, B, C, D. All right, so if A is a 2 by 2 matrix with entries A, B, C, D, what is A inverse? Keeping in mind that we said that not every matrix has an inverse. So it's kind of implied that we mean if it exists. Maybe along the way, we're also going to find out how to tell if a matrix is invertible or not. All right, so I'm expecting, hopefully, that we get a formula for A inverse as its own 2 by 2 matrix. And it's going to be a formula that somehow involves A, B, C, and D. I'm expecting it probably involves all 4 of them, right? You need all the information from A in order to find its inverse. So here's how we're going to handle this. Let's say we know that the inverse should also be 2 by 2. In order for the matrix multiplication to be defined, it has to be, for A times A inverse equal I, this has to be 2 by 2. So let's give this some letters also. I'm going to use the letters at the end of the alphabet, W, X, Y, Z, just because we already used the letters at the beginning of the alphabet. Then we want to find W, X, Y, and Z so that I would like to find it so that when you multiply A inverse times A, the result is the identity matrix. I'm hoping that I can find formulas for W, X, Y, and Z, and maybe there'll be like little formulas where each one of them is in terms of A, B, C, and D. That way I could use the original matrix to find the inverse. Well, we could do the matrix multiplication on the left-hand side here. We know how to do that. W times A plus X times C, W times B plus X times D, etc. I'm going to do that, but I'm going to write each pair, I'm going to kind of write in alphabetical order. Here's what I mean. For this upper left entry, we're doing W times A, but I'm going to write it as A times W. And then we do X times C, but I'm going to write it as C times X. Just because when you multiply real numbers, it doesn't matter what order you multiply them in. Let's just keep it kind of alphabetical. All right, and then over here you get BW plus DX. Down here you get AY plus CZ. Remember we did that warm-up problem at the beginning, so we know how to multiply 2 by 2 matrices. That's what you get on the left-hand side. The right-hand side is still this. Now, do you remember that in the previous lesson, we said that if two matrices are equal to each other, they must have exactly the same entries in exactly the same positions. So we must have AW plus CX must equal 1. BW plus DX must equal 0. AY plus CZ must equal 0. BY plus DZ must equal 1. All four of those things have to be true. Maybe we can figure out little formulas based on this. So I'm going to move the top page, move some of this away. All right, so what we just arrived at, actually, I wrote these 4 little equations, but maybe I should have written all 4 of them like one on top of each other, and we could call it a system of 4 equations. It's kind of a system of 4 equations with 4 unknowns. The unknowns are W, X, Y, and Z, and we're assuming that we were given A. So we were given lowercase a, b, c, d. So it's 4 constants that we know and 4 constants that we're trying to find. So yeah, it's like a system of 4 equations with 4 unknowns. Here's what we're going to do. Instead of writing it as one big system, I'm going to write it as 2 systems. I'm going to focus on the equations from the first row, which are this and this. And the equations from the second row are AY plus CZ, BY plus DZ. All right, so that equals 0 and that equals 1. The reason why I'm splitting it up into 2 smaller systems is because the one on the left is basically a system of 2 equations with 2 unknowns, W and X. The one on the right is a system of 2 equations with 2 unknowns, Y and Z. So it seems easier to work with these as separate problems instead of one really big problem. But let's focus actually just on the one on the left here. Let's draw a big arrow, I guess. Let's focus on this one. What would we do if we wanted to solve this system? I'm saying we know A, B, C, and D, and we want to find W and X. Well, we learned about solving systems by writing the augmented matrix of the system. So we could write A, C, 1, B, D, 0. Right? That's the augmented matrix for this system. We could try to do Gaussian elimination, turn this into a system that's in triangular form or row echelon form, right? And we could try to get solutions for what is W and what is X, probably in terms of A, B, C, D. So here's an idea. Let's multiply. Like, we have to figure out, how are we going to get rid of, we're used to doing this with actual numbers in it. How are we going to do this with actual letters? So what I'm going to do is I'm going to multiply row 2 by a constant. The constant that I'm going to multiply it by is A over B. And, we're allowed to multiply by a constant. So what I'm going to do gets me, row 1 has not changed. Row 2 has been multiplied by this constant. So b times a over b gets me a. D times a over b, I'll write that as ad over b, and 0. The reason why I did this step is because now in column 1 we have a and we have a, so I think if I add a multiple of one row to another, specifically if I add -1 times row 1 to row 2, -1 times row 1 is getting added to row 2. That's going to get me a 0 in that spot. So let's write the first row, which has not changed. But that's going to get me a 0 here. That's why I did this. Aiming for triangular form. Well, what does that do to this other term? AD over B gets -c added to it. So AD over B minus C. And then what happens to the 0? It gets -1 added to it, so -1. Well, we could try to do more of these steps and try to simplify it further, but really we did enough. We wanted to get a 0 here. Now it's a system that's in triangular form, so we're supposed to be able to solve it using back substitution, right? So now we could say row 2 says, as an equation, what does row 2 represent? We went from the equations to the augmented matrix. Now I want to go from the matrix back to equations. Remember how each of these equations has the unknowns w and x. So I know that in the previous lessons, when we were solving systems, usually the unknowns were called x, y, and z. This time the unknowns are called w and x. So the first column kind of represents w's, and the second column kind of represents x's. So row 2 as an equation says AD over B minus C times X equals -1. There's basically 0W plus this times X equals -1. Let's remember, what are we trying to do here? We're trying to find W, X, Y, and Z. We could use this to find X. We could say X is -1 divided by this thing that was in parentheses. I mean, it's a little messy, but it's true. X does equal this. But I have a fraction inside a fraction, so what I'm going to do to fix this up is I'm going to multiply by b over b. If I multiply this by b over b, here, I'll show you. Let's just do it. B over b. That's going to simplify it, right? So x equals, the numerator becomes -b. The denominator becomes AD minus BC. And I like this better because it doesn't have any fractions inside of a fraction. Well, we kind of did part of what we were looking for. I'm going to remind you, what are we working towards here? Let's remember how this conversation started. We're given a matrix A, B, C, D. We want to find a formula or a set of formulas for A inverse. So we want to find W, X, Y, and Z. And I told you that I was expecting that they would probably be in terms of the original letters, A, B, C, D. Well, look what we just found. We found X in terms of A, B, C, D, and D, right? It has all 4 of them. Not in order, but yeah, it has all 4 of them. Could we do this to find the other ones, like W? Yeah, we could find W and the others. So instead of going through all those steps and deriving all of them, I'm just going to tell you that you could use similar steps or a similar strategy to find all four of them, it turns out that W equals D over AD minus BC. X is the one we found, negative B over AD minus BC. Y is going to equal negative C over AD minus BC. Hey, it looks like they all have the same denominator. Z is A over AD minus BC. So what does this mean? If we're given a 2x2 matrix, can we kind of use this to find the inverse? I think so, yeah. So here's what I'll say. The result. And we're also going to summarize this at the end. But the result so far is if A equals ABCD has an inverse, it is well, it's this whole big thing, right? D over AD minus BC, negative B over AD minus BC, negative C, etc. That's the results so far. Oh, you know what? We could write this in a nicer way, though. That's what we're going to do next. Because all four terms have the same denominator. And the denominator is really just a number. So I'm going to say which can be written as. So here's an idea. That denominator, we can pull it out front as a constant. I mean, it's a denominator, so we should write it as 1 over. 1 over AD minus BC times, and now we can just write the numerators. D minus B minus C, A. So that's not so bad. It looks a little bit better now. This right here, 1 over AD minus BC, is a number times a matrix. So this is like a scalar multiplication like we talked about last time. A number times a matrix. This number, AD minus BC, that seems to be coming up over and over again, is so important that it has its own name. The number AD minus BC is called the determinant of A. We write det A equals AD minus BC. The determinant of A equals AD minus BC. So if you're given a 2x2 matrix, you can see what A, B, C, and D are. They're just the four entries of the matrix. And then you could do this little AD minus BC thing to find the determinant of A, which winds up being a part of the formula for the inverse. There's a couple of other ways that we write it besides det A. We also sometimes write, you could write determinant of, and then actually write out the matrix. I mean, it still equals AD minus BC, but, you know, instead of calling it capital A, you could just write out you could write out the matrix with the brackets. Or there's also another way to write it, which I probably won't use very much in this course, but I wanted to let you know just in case you see it. Sometimes when we're talking about the determinant of a matrix, we just write the matrix, but instead of writing square brackets, we just write these vertical bars. So this last line that I wrote, this means the determinant of this matrix. It's a subtle thing because it looks like we wrote a matrix, but instead of writing the square brackets, you just put vertical bars. They almost look like absolute value bars, but it's not really absolute value. So if you just see those bars like that, it's talking about the determinant of what's inside, which we know is AD minus BC. I have a fact to tell you about inverses and determinants. So A inverse exists whenever the determinant of A is not equal to 0. All right, it's important to us that the determinant is not 0 if there's going to be an inverse, because we wrote above that if the matrix A has an inverse, it follows this formula. Well, the determinant is a denominator, right? Denominators should not be 0. So that's kind of the criteria for whether or not A inverse exists. Are we dividing by 0? If we would be dividing by 0, then we just say A inverse does not exist. Or we would say A is not invertible. Now, I'd like to summarize some of what we just said. Summary. If a 2 by 2 matrix, A, B, C, D, has its determinant not equal to 0, then A inverse is equal to, I'm going to write what we wrote above, but instead of writing AD minus BC, I'm just going to write 1 over determinant of A. And then we write D minus B. I'm copying what we had above, right? Where the determinant of A stands for AD minus BC. Let's put a box around this. And also I'll say that if the determinant of A does equal 0, then A is not invertible. So that's a good summary of what we found out, what we derived. All right, so there's a formula for the inverse of a matrix, and it relies on the determinant, which has this little formula, AD minus BC. As far as remembering the formula for the determinant, I think that the AD minus BC is easy to remember, because if you look at the original matrix, look at where AD is. They're kind of diagonal. And look at where BC is. They're like the other diagonal. So you kind of take this diagonal minus this diagonal. AD minus BC. If you do that a few times in a few problems, then you just get used to it. But I guess for this, you also have to remember, like, where do these all go? I guess something that you could kind of notice is that if you compare the original matrix with the formula for the inverse, it looks like A and D swapped places. And it looks like B and C stayed where they were, but they now have minus signs in front of them. And that's how it is, because that's what we derived. But yeah, like the A and D look like they swapped places. The B and C got negatives in front of them. And then determinant in front. All right, now what we just said is all for 2 by 2 matrices. If we have time at some point, maybe we'll discuss determinants and inverses for 3 by 3 matrices. But for now, I'll just tell you that a similar concept does work. I mean, we can't use this formula for a 3 by 3 matrix because this is not 3 by 3, but there is, similar idea behind it all, even though we're focusing on the 2 by 2 case. Let's see, we should do some problems now. All right, so we'll do some example problems. I'll do the first one. Hey, you know what I think would be a good example? Earlier in the lesson when I showed you a matrix and I showed you its inverse, I didn't really tell you how I found it. Well, now you know how I found it. So let's do this as an example. I'll walk us through this first one. So it's going to say, given A equals 3, 1, 4, 2, find A inverse if it exists. All right, so I know what the answer is from earlier in the lesson, but we are going to actually find it. We're going to use this formula, this idea of the determinant. So looking at the 3, 1, 4, 2, we're going to think of them as A, B, C, D. So first, the determinant of A is A, D minus B, C. So this is 6 minus 4, which is 2. Just as a quick note, you don't have to write this in a problem, but you would do a quick check and say, note, the determinant of A, which we found to be 2, it is not equal to 0. So A inverse does exist. Okay, the determinant is not 0, so we can continue the problem and we will find an inverse. So A inverse equals 1 over the determinant, which we found to be 2, times... All right, now we have to use this like D minus B minus C, A, which I said you could kind of think of as A and D swap places, and B and C stay where they are, but they get minus signs in front of them. But to finish this, we should actually do this multiplication. I mean, this is a scalar multiplication, right? Like a number times a matrix. We talked about that in the previous lesson. So 1/2 times 2 is 1. 1/2 times -1, we get -1/2. 1/2 times -4, we get -2. And 1/2 times 3, we get 3/2. So this is the answer. This is A inverse. I'm going to move away the formula other page now, but yeah, so that's how you would do it. That's how you would do this kind of problem. And if you looked back in your notes from earlier in the lesson, that's what I said that the inverse was. And now you see how I got it. I got it with this method. So how about I give you a couple of problems to try? All right, you are going to be given 3 matrices. 2, 3, 4, 5. B equals 1, 3, 2, 6. And I. We know what I is. It's the identity matrix, but we're actually going to use that as one of the problems. So given these 3, I'm going to say... is A invertible? If so, find A inverse. There's going to be 3 parts to this. I think you can guess what they are. Is B invertible? If so, find B inverse. And is I invertible? If so, find I inverse. So I'd like you to pause the video and try this out. All right, so let's get started with part A. So is A invertible? Well, we could check the determinant, right? So the determinant of A is the determinant of 2, 3, 4, 5. And using that AD minus BC, it's going to be 2 times 5 minus 3 times 4. So 10 minus 12. Really, I'm just checking to see if this is 0 or not. It is not equal to 0. All right, so not equal to 0. So A is invertible. And now the problem says to find A inverse. A inverse is going to be 1 over the determinant, so I'm glad that I found it, because we need it anyway, times 5, negative 3, negative 4, 2. All right, so multiply negative 1/2 times each of these numbers. You get negative 5/2, positive 3/2, positive 2, and negative 1. And that's the answer for part A. Oh, by the way, remember, note, if you want to, you can check that A times A inverse equals I. That was in the original definition of an inverse, right? And if you check that, then you would be 100% sure that you found the correct inverse. But it's optional whether you check it. As long as you did these steps carefully, it will be the correct inverse. Okay, part B is the matrix B invertible. So let's look at the determinant of B. So this is going to be the determinant of 1, 3, 2, 6. So I'm thinking of 1 times 6 minus 2 times 3. All right, so look at this. We got 6 minus 6, didn't we? So this is 0. And the determinant of B is 0. So B is not invertible. And that's it. That's the answer to the question, because we can't find the inverse if it's not invertible. So I wanted to make sure that you saw at least one problem like that. And then finally, part C asks us for the, well, it asks us not for the determinant, it asks us for the inverse, but I'm going to go ahead and start with the determinant, because that seems to be helping us with these problems. So 1, 0, 0, 1. So this is 1 times 1 minus 0 times 0. So this is 1. 1 is non-zero, so I is invertible. The determinant, not the determinant, but the inverse of I is 1 over, the determinant we found is 1. Okay? 1 over 1. And then times, look what happens to this matrix when we use the formula. So you wind up with 1, 0, 0, 1, don't you? It's like A and D swapped places. B and C got negatives in front of them, but negative 0 is 0. So you just get the identity matrix again. That is the answer to part C. So what we just found is that the identity matrix is its own inverse. All right? All right, so Yeah, I think this makes sense because if you think about it, I times I inverse should equal I by the definition of inverse. So yeah, the identity matrix is its own inverse. So I think we're going to wrap things up here. Let's just give you a chance in case you're writing any of that. All right, so that was our lesson on inverses of matrices. I guess the important definitions from this section would be the identity matrix, the inverse of a matrix, and the determinant of a matrix. Remember, the determinant is just a number, but it helps tell us whether or not a matrix is invertible. Everything we did seemed like we focused on the 2 by 2 case, and I mentioned in the middle of the lesson, but I want to say this again. These kinds of concepts also apply to larger cases. If we have time at some point, maybe we'll come back and revisit that to look at some 3 by 3s, but I'm satisfied that we covered this for 2 by 2s. So the main type of question that I'm interested in right now would be if I give you a 2 by 2 matrix, can you tell me yes or no, is it invertible? And show work to explain why. And if it's invertible, then find its inverse. You know, if you're given A, find A inverse. If you're given B, find B inverse. And I think we can do that. We just did a few problems like that. So that's going to be it for this one. And everybody, hope you're doing well. And I'll see you soon.